Hello, everyone. My name is Macy Coleman. Today, my partner Amanda McElroy and I will be presenting our tech talk on agent-based modeling and its role in simulation. What if every patient, every provider, every decision could be simulated? Not individually, but all at once. Welcome to agent-based modeling. In combat, each casualty is an agent. Their injuries evolve over time. Interventions, like a tourniquet, change outcomes. Agent-based modeling tracks how timing and treatment affect survival across the entire battlefield. In hospitals, patients, staff, and resources are all agents. Each movement, triage, treatment, discharge affects the system. Agent-based modeling reveals where delays happen and how to fix them. Across populations, individuals interact. Each contact becomes a potential infection. Agent-based modeling shows how disease spreads and how interventions slow it. Agent-based modeling reveals how interactions create outcomes. From a single patient to an entire system, better decisions start with better simulations. Today, we will explore agent-based modeling, examining how it relates to modeling and simulation, how it is used in practice today, why it is important, and where it is headed in the future. So agent-based modeling in healthcare modeling and simulation is a computational approach that simulates the actions, interactions, and autonomous behavior of individual entities within a healthcare system to understand complex system-level outcomes. Unlike traditional top-down modeling, agent-based modeling takes a bottom-up approach, allowing individual agents, such as patients, doctors, nurses, or even viruses, to follow specific program rules and react to their environment. The core components of agent-based modeling are agents, defined as individual entities such as patients, clinicians, age, health status, location, or other resources. Environment. In the healthcare setting, this is where agents interact like a hospital or community. Rules or behaviors. This is where each agent follows behavior rules and makes decisions. Interactions. The model focuses on the interactions between agents, like patient-doctor consultations, and between agents and their environment, like bacteria spreading in a hospital room. And emergence. The core power of this technology lies in observing emergent results, system-level patterns like the spread of a pandemic or a bottleneck in an emergency department that arise from individual interactions rather than being explicitly programmed. The agent-based modeling process first step is defining the agents. This step establishes who or what exists in the simulation and what makes each agent unique. The second step is setting the rules and building the environment. Rules drive behavior. This is where we model decision-making such as triage or treatment priorities. The environment shapes how agents behave and interact. It adds realism and constraints to the system. The third step is running the simulation. This is where the model comes to life. Agents act simultaneously and complex behavior begins to emerge. The fourth step is analyzing results. Analysis reveals insights that aren't obvious up front. This is one of agent-based modeling's biggest strengths. The final step is applying insights. The ultimate goal is action, using simulation insights to improve performance, readiness, and outcomes. So relation to modeling and simulation, agent-based modeling is a powerful method within modeling and simulation that represents systems through individual agents. Each agent operates based on defined rules, behaviors, and decision-making processes, interacting with other agents and the surrounding environment. These interactions generate emergent patterns, allowing us to better understand how complex healthcare systems function in real-world conditions. What makes agent-based modeling particularly valuable in modeling and simulation is its ability to capture realistic human behavior, variability, and uncertainty, factors that are often difficult to represent using traditional models. In healthcare, this means we can simulate patient flow, provider decision-making, and system stress under varying conditions. Most importantly, agent-based modeling supports predictive analysis and planning. By simulating both routine operations and unexpected scenarios such as mass casualty events or resource shortages, healthcare leaders can identify vulnerabilities, optimize resource allocation, and build resilience into workforce and operational planning. Agent-based modeling bridges the gap between individual human behavior and system-level outcomes, making it one of the most powerful tools in modern healthcare simulation. Now I will pass it off to my partner, Amanda McElroy, and she would discuss how agent-based modeling is used today, why it is important, and the future of agent-based modeling.
How it is used today. Today, agent-based modeling is already being used across several areas in healthcare and military medicine. One major application is in hospital operations and patient flow modeling, where individual patients are simulated moving through systems like emergency departments or clinics. This helps identify bottlenecks, optimize staffing, and improve efficiency. Another important use is in infectious disease modeling, where agents represent individuals in a population. These models simulate how diseases spread based on movement, behavior, and interactions, and were widely used during COVID-19 to inform public health decisions. Another key application is in resource allocation, where agent-based models help determine how limited resources, like staff, equipment, or beds, should be distributed. In military medicine, this becomes even more critical. For example, when planning casualty evacuation or resource support across different roles of care, agent-based modeling can simulate how delays or constraints at one level affect the entire system. It is also being explored in policy testing, where leaders can simulate the impact of different decisions before implementing them in real life. So instead of reacting to problems after they occur, agent-based modeling allows for more proactive and informed planning. Additionally, agent-based modeling is being incorporated into training environments where agents create more dynamic and adaptive simulation scenarios rather than relying on fixed, scripted cases. Here's a real-world example of agent-based modeling applied to infectious disease spread in a confined environment. This model simulates how COVID-19 spreads inside a bus, where each passenger is treated as an individual agent with their own position and interactions. What's important here is that no single system is controlling the outcome. Instead, each agent follows simple rules, like proximity to others, and the overall spread emerges from those interactions. This is a key feature of agent-based modeling. Complex system behavior emerges from many small, local interactions rather than top-down control. In this case, the model allows us to visualize how quickly infection can spread in a crowded environment and how factors like seating arrangement or density influence that spread. This is how agent-based modeling is used in healthcare today, helping predict disease transmission, evaluate risk, and test interventions like spacing, masking, or ventilation before applying them in the real world. Why it is important. Agent-based modeling is important because it allows us to better understand complex systems that don't behave in predictable ways. Healthcare systems are made up of multiple interacting components: patients, providers, logistics, and resources, all influencing each other in real time. Traditional models often simplify this complexity, but agent-based modeling allows us to actually simulate it. Another reason agent-based modeling is important is that it helps bridge the gap between theory and real-world application. In many cases, decisions are made based on experience or assumptions, which are valuable but don't always capture the full complexity of a system. Agent-based modeling provides a way to test these assumptions in a controlled, simulated environment before applying them in real life. This becomes especially valuable in military medicine, where leaders are making decisions in uncertain, high-stakes environments. Agent-based modeling allows those decisions to be tested first, reducing risk and improving outcomes. It also helps uncover patterns that aren't immediately obvious, like how small inefficiencies or delays can create significant downstream effects. So ultimately, agent-based modeling improves situational awareness, planning, communication, and decision-making. The future. Looking ahead, the future of agent-based modeling is closely tied to advances in artificial intelligence, data integration, and computing power. One major direction is the integration of agent-based modeling with real-time data, which would allow simulations to continuously update as conditions change. This could support near real-time decision-making in both clinical and operational settings. Another important development is the combination of agent-based modeling with digital twins, where entire healthcare systems are modeled as dynamic simulations. In this case, agents operate within a larger system model, allowing leaders to test decisions on a virtual version of reality before implementing them. As computing power continues to improve, these models will be able to handle more agents, more variables, and more complex interactions. We're also seeing increased integration with machine learning, which allows agents to become more adaptive and realistic over time. In the future, this could lead to simulations that not only predict outcomes, but also continuously learn and improve as more data becomes available. This has significant implications for both healthcare systems and military operations, where adaptability and responsiveness are critical. In military medicine, this has the potential to improve planning, readiness, and decision-making at both the unit and system level. An example of where this is going is the Roll4 modeling tool, which is currently being developed at the Defense Health Agency. It's essentially a digital twin of a healthcare system, allowing planners to simulate patient flow, resources, and outcomes at scale. What makes it powerful is that it doesn't just model the system structurally, it incorporates agent-based modeling, meaning individual patients, providers, and resources can behave dynamically within that system. This is especially relevant to today's focus of large-scale combat operations, or LSCO, which are known to create casualties that overwhelm our Role 2 and 3 with large patient streams. As these technologies continue to evolve, agent-based modeling will likely play a larger role in how we design, test, and optimize our complex systems. To summarize, agent-based modeling is a powerful tool that allows us to simulate complex systems by focusing on individual behaviors and interactions. It provides a more realistic way to understand how systems function, especially in environments where variability and unpredictability are important. It is already being used today in healthcare operations, disease modeling, and military planning, and its role will continue to grow as technology advances. Ultimately, agent-based modeling supports better decision-making by allowing us to test and understand systems before applying those decisions to the real world.